Welcome to this explainer. Today, we are fundamentally shifting our perspective. I want you to stop looking at the ocean as just a massive, passive body of salt water. Instead, we're going to look at it as a finely tuned, highly complex planetary operating system. It is essentially a biomechanical engine that dictates the life support metrics for our entire world. Over the next few minutes, we're going to run a full diagnostic scan on this system. We'll be analyzing the invisible chemical gears and physical firewalls that keep Earth thriving and literally make human life possible.
Okay, let's dive into this. First, we'll look at the planetary life support. Then, tracing oxygen and carbon. Third, ocean pH and buffering. Fourth, the nutrient mixing engine. And finally, global productivity patterns.
Section 1. The Planetary Life Support, Earth's Marine Operating System. Now, you probably already know that the oceans cover an astounding 71% of our planet's surface. And with an average depth of 3.5 kilometers, the sheer volume we're talking about here is almost incomprehensible. It's enough to fill billions of swimming pools. But what's absolutely vital for our diagnostic today is the surface area. This vast interconnected boundary between the water and the air is where atmospheric gases continuously enter the system. Through constant diffusion and the physical churning of wave action, the ocean literally breathes, taking in the very gases that will power the biological engines deep below the surface.
Section 2. Tracing oxygen and carbon, mapping invisible gas inputs.
As we trace these gas inputs, it's pretty fascinating to note a quirk in the ocean's programming. Its capacity to hold these dissolved gases actually surges when temperatures drop and pressures rise, which has massive implications for the deep ocean. But as we drop deeper into the water column, the sunlight rapidly fades, right? And this creates a hard limit on biological growth. This brings us to a really critical threshold called the compensation depth. Think of it as the absolute break-even point. It's the exact depth where a marine plant's rate of photosynthesis is perfectly canceled out by its own respiration. At this line, which usually hits right where light levels drop to just 1% of surface light, net oxygen production is flat out zero. Below this depth, the system just can't sustainably generate new biological life from sunlight.
And this brilliantly illustrates exactly what happens across those depths. Up near the sunlit surface, oxygen is totally abundant thanks to high photosynthesis. But as we sink past that compensation depth, oxygen levels violently crash, hitting a minimum zone right around the 800-meter mark. Why? Well, because below the sunlit zone, massive amounts of deep-sea animals are still respiring, and dead organic matter is decaying. Both of those processes aggressively consume oxygen and pump out carbon dioxide. As you can see here, that CO2 line just steadily surges as we drop deeper into the dark.
Section 3. Ocean pH and buffering. The system stabilizers.
So we have highly variable inputs of oxygen and carbon dioxide, but marine biology requires a super stable, tightly regulated environment to actually survive. Let's shift our scan over to the chemical metrics to see exactly how the ocean handles this stress. 8.1. That is the ocean's baseline surface pH metric. Now remember your basic chemistry. A pH of 7 is neutral, so 8.1 means the ocean is naturally slightly alkaline. But, and this is crucial, the pH scale is logarithmic. This means that a tiny shift of just one single unit on this scale results in a massive 10-fold increase in hydrogen ions. So maintaining this 8.1 baseline isn't just a preference for marine life, it's a strict requirement for survival. The system literally cannot afford wild swings. To prevent those catastrophic swings, the ocean runs a multi-stage chemical execution step by step. It's basically a stabilizing algorithm. Let's look at how it works. Step 1. As carbon dioxide enters the water, it forms carbonic acid. Step 2. This acid easily breaks apart into bicarbonate and free hydrogen ions. Now, free hydrogen ions are dangerous. They are exactly what make water more acidic. So step 3 automatically kicks in. Calcium carbonate in the ocean breaks down to provide carbonate ions. These act like tiny chemical sponges, eagerly absorbing those dangerous free hydrogen ions to form completely harmless bicarbonate.
And this brilliantly illustrates the full chemical schematic of the carbonate buffering system in action. The system is literally wired to aggressively bind up free hydrogen ions, effectively neutralizing acidifying inputs. It acts as a massive planetary-scale chemical shock absorber. If the water gets too acidic, the reaction shifts one way to soak up the acid. If it gets too basic, it shifts the other way to release it. Honestly, it's an incredibly elegant piece of planetary engineering.
But, the system isn't perfectly uniform. There's a distinct minimum drop-off zone right at 800 meters. Remember our earlier gas data? This low pH zone perfectly mirrors the high CO2 levels we saw at that exact same depth.
All that deep water animal respiration and decay pumps out so much CO2 that it pushes the buffering system to its absolute limits, causing a localized drop in pH before the system eventually recovers further down in the abyss.
Section 4. The nutrient mixing engine, firing the biological engines.
Okay, we've seen the invisible chemical stabilizers. Now let's shift focus to the physical ocean engines and the chemical fuels that actually power massive global plankton blooms. Sunlight is the ignition, sure, but these are the primary fuel types: nitrate, phosphate, and silicate. Without these essential inorganic molecules, photosynthetic organisms simply cannot grow. Every marine plant out there needs nitrogen and phosphate, but some specific, highly productive organisms, like diatoms, actually require dissolved silicate just to build their microscopic, structural glass-like shells. If any one of these fuels runs out in the sunlit zone, the biological engine stalls completely.
The catch is, these nutrients get used up incredibly quickly at the surface. To get more, the ocean relies on physical mixing from the deep. Think of the thermocline, which is a rapid change in water temperature, as a seasonal firewall. In the summer, the sun heats the surface water, making it light and buoyant. This creates a physical barrier that traps the cold, heavy, nutrient-rich water down at the bottom. But in the winter, falling temperatures cool the surface. The water gets heavy and sinks, completely shattering this thermal barrier and allowing the deep, vital nutrients to surge right back up to the surface.
So the crucial point here is how this plays out geographically. If we compare regions, tropical zones have a permanent thermocline. Because it's always hot, that thermal firewall never breaks. The water is highly stable, crystal clear, but biologically barren, because nutrients just can't mix upward. Temperate zones, on the other hand, are dynamic mixing engines. The changing seasons reliably shatter the firewall every single winter, surging massive amounts of nutrients to the surface to fuel explosive spring plankton blooms.
Section 5. Global Productivity Patterns, Analyzing the System Output. Let's zoom back out to a macro-planetary scale. We're going to look at the final, visible biological output of all these hidden chemical buffers and physical mixing engines working together in perfect sync. Looking at this regional breakdown, this system outputs are vastly different depending on what the limiting factors are. The tropics have endless light for sure, but they are severely limited by that permanent thermocline blocking the fuel. Temperate zones have a nice balance of seasonal light and seasonal nutrient mixing. But the polar oceans, they have no thermocline at all. Their waters are deeply mixed and constantly fully loaded with nutrient fuel year-round. They're just simply lacking the light to ignite it. Well, until their short, intense summer finally arrives. Now, what's really interesting about this data readout is when we map these seasonal variations, the differences are staggering. Notice the sheer, towering spike of the North Polar line. Because those waters are so saturated with nutrients, the absolute moment the sun hits, productivity violently explodes upward in one sudden, massive spike. Compare that to the wider double-hump temperate curve. That represents a massive spring bloom, followed by a smaller fall bloom as those seasonal thermoclines lock and release. And flatlining all the way across the bottom? The nutrient-starved tropics. So we've seen just how meticulously designed this marine operating system really is. From the gas inputs and the chemical buffers to the nutrient mixing engines, every single variable is tightly controlled to sustain life. Which brings us to our final system query. What happens when human-induced CO2 emissions completely overwhelm the ocean's chemical shock absorbers? Are we pushing this finely tuned, perfectly balanced planetary machine toward an anomaly it simply cannot internally neutralize? Honestly, that is a data point we are currently forcing the ocean to calculate in real time. Thank you so much for joining me on this explainer.